Hi, I'm Jeff Groh, and this is Differential Equations, Exam 4 Review. On problem 1, we consider the differential equation x dot equals 4, negative 2, 5, 2x. And we were told that one of the eigenvalues is 3 plus 3i with corresponding eigenvector 1 minus 3i, 2. On this problem, you're given everything you need to write down the solution right away. You have alpha equals 3 and beta equals 3. U is the real part of the eigenvector, and W is the pure imaginary part, with the I factored out and eliminated. The solution x is C1 times e to the alpha t, alpha is 3, times cosine beta t times u minus sine beta t times w plus C2 e to the 3t sine 3t times 1, 2 plus cosine 3t times negative 3, 0. As you can see, the only difficulty on this problem is memorizing the formula. On problem 1b, the system of differential equations is x dot equals 5, 4, negative 1, 1, all times x, where we are told that the eigenvalue is lambda equals 3, with algebraic multiplicity 2, geometric multiplicity 1, with eigenvector equal to negative 2, 1. In this problem, we begin by finding the generalized eigenvector. Generalized eigenvectors solve the system a minus lambda I times w equals the eigenvector v. We solve the linear system by setting up an augmented array like this. The original matrix was, I'll write it over here, 5, 4 minus 1, 1. If we're subtracting 3 from the diagonal elements, this gives the augmented array 2, 4, 2, negative 1, negative 2, negative 1. As you can see, if we multiply the second row by 2 and add to the top row, we'll get a row of zeros. If we then multiply the second row through by negative 1 and interchange the first two rows, we get the reduced row echelon form of 1, 2, 1, 0, 0, 0. This gives the equation x plus 2y equals 1. We only need one solution, so we'll choose one. How about the solution 1, 0? We have then the solution to the system of differential equations is C1 e to the 3t is 2 negative 1 plus C2 e to the 3t times t times 2 negative 1 plus 1, 0. On problem 2a, we're told to use the method of undetermined coefficients to solve the linear system x dot equals -2, -2, -5, 1 all times x, plus the forcing term 1, 2 times e to the t. We're told that one eigenvalue is -4 with corresponding eigenvector 1, 1, and another eigenvalue is equal to 3 with eigenvector equal to 2, -5. Homogeneous solutions are x1 equals e to the -4t times 1, 1, and then x2 is e to the 3t times 2, -5. This gives us the homogeneous solution c1 e to the -4t 1, 1 plus c2 e to the 3t 2, -5. From here, we need to find a particular solution. We're using the method of undetermined coefficients on this problem. The method of undetermined coefficients begins with a guess on the form of the particular solution. Since the forcing function looks like e to the t times some vector, we'll choose e to the t times some unknown vector u. That being the case, xp dot will be e to the t times that unknown vector u. Plugging all of this into the differential equation, we have e to the t times u equals the matrix A times e to the t times u plus e to the t times the vector 1, 2. Dividing through by e to the t, we now need to get all the u's on one side and everything else on the other. We get -1, -2 equals au minus u. In order to factor the vector u out on the right-hand side, we need to insert an identity matrix I. This gives us a minus I times the vector u. We need to solve the linear system where we subtract 1 from the diagonal elements of the matrix A. Subtracting 1 from the diagonal elements of the matrix A yields -3, -2, -5, 0. On the right-hand side, we put the vector -1, -2. We now just need to solve this linear system. So, multiplying through by -1/5, row 2 yields a new row 2, gives us -3, -2, -1, 1, 0, 2/5. If we multiply 3 times row 2 plus row 1 yields a new row 1, we'll get 0 in this spot, -2 in this spot. The second row will stay the same. On the last row, since we're taking 3 times this plus this, 3 times this plus this, we'll have 6/5 and -5/5 gives us 1/5. Multiplying through by -1/2, and then interchanging row 1 and row 2, we'll have this in reduced row echelon form. We'll have 2/5 in this spot, since this went up into this spot. Multiplying through by -1/2, we'll have -1/10 in this spot. This gives us the vector u equal to 2/5, -1/10. The solution then is x equals 2/5 -1/10 e to the t plus c1 e to the -4t times 1, 1 plus c2 e to the 3t times 2, -5. Problem 2b asks us to solve the exact same differential equation using the method of variation of parameters. You'll recall that for variation of parameters, we use the formula x equals x integral x inverse f dt plus the homogeneous solution. The particular solution is given by this first part. On this problem, we're solving x dot equals -2, -2, -5, 1x plus 1, 2 e to the t. Lambda equals -4 with corresponding eigenvector 1, 1. Lambda equals 3 with corresponding eigenvector 2, -5. The fundamental matrix is e to the -4t, e to the -4t, 2 e to the 3t, -5 e to the 3t. The first thing we do after writing down the fundamental matrix is we find its inverse. X inverse is 1 over the determinant. That's going to be -5 e to the -t minus 2 e to the -t. That's all out front, which simplifies, by the way, to -7 e to the -t. We switch the diagonal elements, so we have -5 e to the 3t, and in the lower right, e to the 4t. Then we negate the off diagonals, so we have -2 e to the 3t and negative e to the -4t. I'd like to simplify the inverse of the fundamental matrix by multiplying through by this 1 over e to the -t. That's like multiplying through by e to the t instead, because this can come up into the numerator as an e to the t. I would also like to push this negative through. Getting rid of that negative makes most of the terms inside of here positive, except for the one in the lower right. We'll have x inverse equals 1/7. I'll leave the 1/7 out. It's easier to deal with it that way than having a whole bunch of fractions inside of the matrix. 5 e to the 4t, 2 e to the 4t, e to the -3t, negative e to the -3t. I've corrected my transcription error, making this exponent negative. The forcing function was 1, 2 e to the t. We need to calculate x inverse f before we integrate. So performing that multiplication, we'll have 1/7 times 5 e to the 4t, e to the -3t, 2 e to the 4t, negative e to the -3t, times e to the t, 2 e to the t. Multiplying gives us 1/7, which is just coming along for the ride. We'll have 5 e to the 5t plus 4 e to the 5t gives us 9 e to the 5t. And then e to the -2t minus 2 e to the -2t gives us minus e to the -2t. The next step is to integrate x inverse f. This case gives us 1/7 times 9/5 e to the 5t, 1/2 e to the -2t. The particular solution is then x times the integral of x inverse f dt. You'll recall that the fundamental matrix X was e to the negative 4t, e to the negative 4t, 2 e to the 3t, negative 5 e to the 3t. We're multiplying that by this 1/7. Scalars commute, and so this scalar can come out front. 9/5 e to the 5t, 1/2 e to the negative 2t. We have 1/7 times. When we multiply e to the negative 4t times e to the 5t, we get e to the t, as expected. So we'll have 9/5 e to the t plus 1 e to the t. 9/5 plus 1, which is 5/5, is 14/5 e to the t. Here we'll have an e to the t, 9/5 e to the t, minus 5/2, also e to the t. So 9/5 minus 5/2. That's going to be 18 minus 25. The answer will be negative. 18 minus 25 is negative 7/10 e to the t. We'll push the 1/7 in now. We'll have 2/5 negative 1/10 all times e to the t, just as before. The answer is 2/5 negative 1/10 e to the t plus c1 e to the negative 4t times 1/1 plus c2 e to the 3t times 2 negative 5. On problem 3, we're asked to find and classify the equilibrium points to the linear system x dot equals x times 1 minus x minus y, y dot equals y times 4 minus 2x minus 8y. We also are asked to discuss the stability of each equilibrium point. To find the equilibria, we set the right-hand sides equal to 0. So, setting the right-hand side of the first equation equal to 0, we get x is 0 or x plus y equals 1. Setting the second equation equal to 0, by the way, this and this must be true, y equals 0, or, notice that all of these are divisible by 2. I can write that as x plus 4y equals 2. There are 4 ways to combine these, and hence 4 equilibrium points. We can have x equals 0 and y equals 0, giving us an equilibrium point at 0, 0. Alternatively, we can have x equals 0 and the other equation holding, which would give us y equals 1/2. If y is equal to 0, we can have x equal to 1, and that leaves only one other possibility. We can have these two linear equations hold simultaneously. To solve this linear system, we might subtract x minus x, the x's would go away, 4y minus y is 3y, and then 2 minus 1 is 1. We get y is 1/3, and if y is 1/3, then x must be 2/3. That gives us the fourth equilibrium point, 2/3, 1/3. Remember that to classify the equilibrium points, we need to find the matrix which linearizes these. To do that, we'll distribute the x and the y on these terms so that we can calculate the partial derivative matrix simply. The partial derivative matrix is then calculated. We'll calculate the derivative of each term on the first row with respect to x, which is 1, minus 2x, minus y. Make sure you understand how to calculate those partial derivatives. We then calculate the derivative with respect to y of the same thing. When we take the derivative with respect to y, we hold x constant, which means the derivative of x with respect to y is 0. Similarly, the second term has derivative 0. When we take the derivative of the last term with respect to y, we're holding x constant, and so we get negative x. Taking the derivative of the next row with respect to x gives us negative 2y. And then taking the derivative with respect to y, we have 4 minus 2x minus 16y. We're now able to classify the equilibrium points and their stability. Evaluating the matrix of partial derivatives at 0, 0 yields 1, 0, 0, 4. This matrix is diagonal, which means the eigenvalues can be read right off of the diagonal of the matrix. They're all positive, which means this is a source, and sources are always asymptotically unstable. Evaluating the matrix of partial derivatives at 0, 1/2, x is 0, y is 1/2, we'll have 1/2, 0, y is 1/2, we'll have negative 1 here, x is 0, y is 1/2, we'll end up with 4 minus 8, which is negative 4. In this case, the eigenvalues are 1/2 and negative 4. The matrix is lower triangular, and hence the eigenvalues are read directly off of the diagonal. Since 1 is positive and 1 is negative, this equilibrium point is a saddle point. Saddle points are always just unstable. Evaluating the matrix of partial derivatives at the equilibrium point 1, 0, x is 1, y is 0, we'll have negative 1, negative 1, 0, and then if x is 1 and y is 0, we end up with 2 here. This matrix is upper triangular. We read the eigenvalues directly off of the diagonal. We see that this is a saddle point, and that is unstable. Evaluating the matrix of partial derivatives at the equilibrium point 2/3, 1/3. If x is 2/3, we'll have negative 4/3 here, plus 1, 3/3 gives you negative 1/3. Minus another 1/3, we have negative 2/3. Negative 2/3, and then plugging in 1/3, we get negative 2/3, and then 2 times 2/3 is 4/3, we have negative 4/3, plus 12/3. 12/3 minus 4/3 is 8/3, minus 16/3, we end up with negative 8/3. In order to classify this equilibrium point, we need to find the eigenvalues of this matrix. The eigenvalues are going to involve a little more work than in the last three cases because this is not diagonal, upper triangular, or lower triangular. Finding the eigenvalues by the old-fashioned way we'll set 0 equal to the determinant of the matrix that is obtained by subtracting lambda from the diagonal elements. You can see that we get 0 equals negative 2/3 minus lambda, negative 8/3 minus lambda, and then we subtract the product of these two negative values, which is going to be 4/9. Foiling this out, we'll get a positive lambda squared. We'll have positive 2/3 plus 8/3, that's 10/3 lambda. We'll have a positive 16/3 minus 4/3 gives us, we'll have positive 16/9 minus 4/9. That's going to be plus 12/9. Notice that 12/9 reduces to 4/3. We can now solve this using the Pythagorean. We can now solve this using the quadratic formula. Lambda is negative b plus or minus the square root of b squared minus 4ac. Maybe it's better to leave that as 12/9. All over 2a. You can see that we're going to have here 100/9 minus 48/9. That's going to give you 52/9. The square root of 52 is bigger than 7 but less than 8. And so you're going to end up with something bigger than 7, less than 8 divided by 3 here. When we subtract, it's going to be negative. Negative minus something, a positive, will be negative. When we add, it's still going to be negative because the numerator is between 7 and 8. That means these are both negative, which means that the equilibrium point is a sink. And sinks are always asymptotically stable. Problem 4 is the last problem, and it has 3 parts. On each part, we're asked to find the eigenvalues and to state their algebraic and geometric multiplicities, and also find the eigenvectors. On the first problem, we're given the matrix 1, 1, 1, 1. First, we find the eigenvalues. To do that, we set 0 equal to the determinant of the matrix obtained by subtracting lambda from the diagonal elements. This gives us 1 minus lambda quantity squared minus 1. That's going to be lambda squared minus 2 lambda plus 1 minus 1, which cancels. Factor lambda out, and we see that we have 2 eigenvalues, 0 and 2. Each of those has algebraic multiplicity 1. Since the geometric multiplicity is always at least 1, and less than or equal to the algebraic multiplicity, we now know that the algebraic multiplicities are both 1, and hence the geometric multiplicities are also both 1. We have only to find the eigenvectors. For lambda equals 0, we solve the augmented array. Notice you can always cross this second row out in the 2 by 2 case. We end up with the equation x plus y equals 0, and hence we find an eigenvector 1, negative 1. You can switch them and negate 1. Since the eigenspace is one-dimensional, we see also again confirming that the geometric multiplicity is 1. So we have algebraic multiplicity equals 1, geometric multiplicity equals 1. For lambda equals 2, we subtract 2 from the diagonal elements, and abut that next to the vector 0, 0 in an augmented array. You can clearly cross the coordinates out, flip and negate to get the eigenvector 1, 1, which you might have seen by inspection from the beginning. Again, a one-dimensional eigenspace. We had algebraic and geometric multiplicity equal to 1. On part B, we have the matrix 4, -5, 2, -3. We begin by finding the eigenvalues by subtracting lambda from the diagonal elements and taking the determinant and setting it equal to 0. We have 4 minus lambda, -3 minus lambda, and then plus 10, because we're subtracting the -10. We'll have a positive lambda squared. A -4 lambda and a plus 3 lambda is minus lambda. -12 and 10 is minus 2. You can see that this will factor as lambda minus 2, lambda plus 1. This gives us eigenvalues -1 and 2. Again, since both of these have algebraic multiplicity 1, they will have geometric multiplicity as 1 as well. You might be able to see that for lambda equals -1, the eigenvector will be 1, 1, but we'll do this the old-fashioned way as well. We need to subtract the eigenvalue from the diagonal elements. When we subtract -1, it's like adding 1. So we have 5, -5, 2, -2. You can see then that our eigenvector will be 1, 1. You can switch these and negate 1, but you can also rescale them, and I'll choose 1, 1 as my eigenvector. Again, one-dimensional, so we have algebraic and geometric multiplicities equal to 1. For the lambda equals 2 case, we subtract 2 from the diagonal elements. And you can see that we get an eigenvector 5, 2. Switch and negate 1. Again, algebraic and geometric multiplicities are 1. On part C, the matrix is 1, -2, 2, -2, 1, -2, 2, -2, 1. We first find the eigenvalues. To do that, we set 0 equal to the determinant of the matrix obtained by subtracting lambda from the diagonal elements. To calculate the determinant of a 3 by 3, there is a special method. One common strategy is to duplicate the first and second columns and then multiply down diagonals like this. We'll have 1 minus lambda cubed plus 8 plus 8. Next, we subtract products going the other way. So we get minus 4 times 1 minus lambda, minus another 4 times 1 minus lambda, and minus 4 times 1 minus lambda. These last three terms can be expressed as minus 12 times 1 minus lambda. We now need to FOIL out this perfect cube. You might see that this will be minus lambda cubed plus 3 lambda squared minus 3 lambda plus 1 using Pascal's triangle. You can figure that out. Plus 16 minus 12 plus 12 lambda. We'll combine like terms to get minus lambda cubed plus 3 lambda squared. Here we have 12 lambda minus 3 lambda is going to be plus 9 lambda. 17 minus 12 is plus 5. I'll multiply through by a negative so that my leading coefficient is positive. Lambda cubed minus 3 lambda squared minus 9 lambda minus 5. We need to solve for the roots of this cubic. A simple way to find those roots is synthetic division. Using the rational root theorem, you can see that the only possible rational roots are plus or minus 1 and plus or minus 5. You take the divisors of the constant term and divide by the divisors of the leading coefficient. In this case, the leading coefficient is 1. So you take 1 over 1 and 5 over 5, plus or minus on both. You can see pretty quickly that 1 doesn't work, so you might try negative 1 instead. Bringing the 1 down, you multiply and add. Multiply and add. Multiply and add. Since we get 0, we've found a root. We can see now that this factors as lambda plus 1 times lambda squared minus 4 lambda minus 5, using these as the coefficients of the quadratic that forms the quotient. This last factors as lambda minus 5 times lambda plus 1. You can see that it has to have opposite signs that add up to negative 4. So you get lambda minus 5, and we'll add the extra factor of lambda plus 1 onto the other one. You can see that lambda equals negative 1 with an algebraic multiplicity equal to 2. Lambda equals 5 with an algebraic multiplicity equal to 1. We now need to find the geometric multiplicities and the eigenvectors. Keep in mind, our original matrix A is 1, negative 2, 2, negative 2, 1, negative 2, 2, negative 2, 1. Lambda equals 5 looks like it's easiest to work with. The algebraic multiplicity is 1, so you're guaranteed that the geometric multiplicity will also be 1. So let's work with lambda equals 5 first. For lambda equals 5, we need to subtract 5 from the diagonal elements. And put that next to 0, 0, 0. Performing elementary row operations, let's multiply the second row by 1 and add to the second row. Let's multiply row 3 plus row 1, row 2 yields a new row 2, and also 2 times row 3 plus row 1 yields new row 1. We'll do those two elementary row operations. We'll have 2, negative 2, negative 4, and then 0. These last are all going to be 0 still. We'll end up with zeros in these two spots. This plus this is 0. This plus this is minus 6. This plus this is minus 6. 2 times this plus this is 0. 2 times this plus this is minus 6. 2 times this plus this is negative 8, and 2 is minus 6. You can see that we can eliminate one of these rows. Also, multiplying the last row by 1/2, and negative 1/6 times row 2, we'll have 0, 0, 0, 0, 0, 1, 1, 0, 1, negative 1, negative 2, 0. Let's put the bottom row and interchange it with the row 1. That gives 1, negative 2, 0, 0, 1, 1, 0, 0, 0, 0, 0. We're almost in reduced row echelon form. We just need to add row 2 to row 1, yielding a new row 1. This plus this is 0, this plus this is negative 1. You can see that we have y plus z equals 0, and x minus z equals 0. We can make everything depend upon z. Our eigenvectors are going to look like x equals z, y equals negative z, and z is what it is, which means our eigenvectors are going to be scalar multiples of 1, negative 1, 1. You can see that the eigenspace is one-dimensional because they're all scalar multiples of this one vector. That means that the geometric multiplicity is 1, as expected. We have yet to find out what happens in the case lambda equals negative 1, which had algebraic multiplicity 2. Subtracting 1 from the diagonal elements is like subtracting negative 1 from the diagonal elements is like adding 1. As you can see, the last row and the first row are the same. Multiplying the first row by negative 1 and adding to the last row yields a row of zeros. Adding the first row to the second row yields another row of zeros. And then multiplying through by 1/2, we find the reduced row echelon. The reduced row echelon form is 1, negative 1, 1, and then the rest are zeros. In this problem, there's only one constraint on the variables, x minus y plus z equals 0. So you can write x in terms of both y and z. X is going to be y minus z. That means your eigenvectors are going to have the form y minus z, y, and z, which we can separate out as y times the vector 1, 1, 0, plus z times the vector negative 1, 0, 1. It should now be apparent that the eigenspace is two-dimensional. You can go into either of these two directions and end up still in the eigenspace. Since the eigenspace is two-dimensional, the geometric multiplicity is 2. So your eigenvectors, the basis for the eigenspace will be 1, 1, 0, and negative 1, 0, 1.